Chair Satoshi Tojo, and it's a great honor for me to introduce Professor Sagayama. I think he's a big name. Many of you already know that he started his career from the phonetics speech recognition. First, he joined the NTT Lab. NTT is a Japanese national telephone company. And after that, he moved to the ATR, another research institute, and next to the JAIST. And he was a colleague of the JAIST. And after that, he moved to the University of Tokyo. And now he is a Meiji University, and what is the density in English? The University of Electrocommunications. Yes, he's many guest professors. Okay, the career is gorgeous. It's okay. But I personally know him very well. We traveled to Vienna together and see the opera, like that. And one of the most favorite what he has said is he's a professional of the hidden Markov model, HMM. He said that everything in this phenomena on the Earth should be regarded as a HMM. I like it. Okay, let us enjoy his talk.
Thank you very much, Tojo Sensei. It is a great honor for me to be invited in this opportunity. I'm just a very old person, probably the oldest in this conference. So, can you tell what age I am?
17. 17.
17?
No, 17.
17 years, no. My age. So it is 75 years old. Possibly the oldest in this conference. Okay, so that means that I stick to the old knowledge and the old theory, and so it may be boring for you, but let's discuss what is the true way to understand music. Anyway, so okay. Just for credit, so there's the number of names I worked with. And it was quite fortunate for me that I had so excellent students, so many excellent students. Let's see. So as Tojo Sensei on the private company now, I started the music research because it was not I had no freedom to do my music research at the NTT labs. So after being released from NTT, I have freedom this way. And from the 1970s on around that time, I'm fascinated with HMM or hidden Markov model, which is very powerful and applicable to. Of course, it is applied for speech processing first, and then I noticed that this model is applicable to everything, including music, and the music is possibly the better application than speech itself. Okay. So my career is speech processing and the music processing after moving to the university. So this is a quick look at what I was involved in speech and music. So music was a kind of just a small portion for me at first, but now I like music research. Sorry for Japanese. Let's speak it. Okay, so focusing on the music signal processing. It used to be my lab's a major area. So because I was long working in speech area, the speech is a signal, so signal processing is an essential part. And so I started music processing as a signal processing. So we have some interesting results. And one is the harmonic temporal clustering, applying the EM algorithm as just the part of signal processing. So at this time, the EM algorithm is very well known, but it was run beforehand of processing, signal processing. So our research, or Kameoka's research, is the EM algorithm included in the signal processing group. It was at that time it was a new idea. So let me show you the one example. If you have an input music sound like this, it is well known Chopin's nocturne. Okay, and it is decomposed into notes using the HTC, or harmonic temporal clustering. So and if you replace the so it is aimed for automatic music transmission into score. So once the score is obtained, you can assign some MIDI instrument like an ocarina, and it sounds like this. Sorry. PowerPoint has some problem. You possibly some of you experienced the same thing. Okay. Anyway, so this is one topic of music signal processing. So and as the proportion of working areas of my students, the music signal processing was the major part. So another topic is harmonic percussive sound separation, or HPSS. Some of you may know the word of HPSS. I named this topic with the name HPSS. It is one of the common words in music processing. And so though it is a small portion of my lab's activity, we did music information processing, but I enjoyed it very much. And one was automatic accompaniment. So we gave the name of Eurydice, or LVDC in Italian. So it comprises two parts of score following and accompaniment. Accompaniment is just a MIDI player, but the score following is the kind of tricky part of following the players, play the piano something. Players may slow down or skip some part, or go back and drop sharps and flats. And so it is a kind of a very erroneous input to find out where in the score he or she is playing. So this is a good application of Hirata model. But possibly you know Hirata model. It is a probabilistic model that can allow just one output, but a wide range of some distribution, including dropped, sharp dropped, or flat dropped, or slow down, or so whatever. So here is a good demo here. Let's see. Oh, it doesn't work? Oh. it's really the good player, but somehow he includes some errors. It is most of the duo piece. So the system works in this way. Okay, this is a good example of how hidden mark model is powerful in our. Okay, so hidden mark model. What is hidden mark model? It is it comprises the hidden states of the machine states, and every time clock, it has a self loop or a transition to other states, like this one, and skip on this one to go to this. So this is a very simple illustration of a hidden mark model, and the outcome is in this figure. It is on a set output type to have a speech spectrum originally with some probabilistic distribution. So it is not definite. It is vague. And this is a time. This is related to timing, but with the self this state can be lengthened anywhere with some probability. So this is the simple idea of the hidden mark model, and it is a generative model to produce how speech is produced. Speech, just like I'm doing, is a process of taking the time progresses and output from the specific states, and so the spectrum is not definite, not always the same. It has some distribution. So this is a very good model of how speech is produced. Okay, and the first use of hidden mark model was speech recognition in 1960s. That was a very good work, and the formation was that inverse problem. So we observed a sequence of speech spectrum, and inverse problem can find the maximum likelihood transition history. You can think of this sequence, multiple sequences like konnichiwa or sayona or whatever. So several words, and you can calculate the likelihood through this way or another word, and so you can compare, and as a result you can find the most likely word which has been possibly spoken. It's not determined. So this is a very good way of including the double probabilistic model, that the state transition is probabilistic and the output is also probabilistic, and made the problem in an inverse problem which can be solved with a maximum likelihood principle. So very smart way. And current speech recognition technology is also based on this. But the probabilistic distribution is replaced by machine learning or nonlinear networks. So that is a very high accuracy of speech recognition. And after this, hey, this is a generative model. Why don't we generate speech? So some people use this problem as a forward problem to produce the speech. Okay, so this is a speech synthesis, hidden HMM speech synthesis, and used in a text-to-speech system. So what's next? Of course, we will think about it. I thought that HHM will be quite useful in music. So in this framework, hidden code progression may exist under the behind this model. And the hidden code progression, like in some code, the next code, emits melodies onto the sequence of notes. Okay, so this figure can be interpreted as a melody generation model from the underlying code sequence. Okay, so but my first application was the inverse problem, like a speech recognition. So my student worked on an inverse problem with this music model to find out the code, underlying hidden code sequence, given the melody. So given the melody is given, the underlying hidden code sequence is revealed. What does it mean? It is an automatic arrangement from a single tone melody to a free chord arrangement. Okay, so I enjoyed this work, but after that, I thought that the hidden model can work as a forward program, just like HMM speech synthesis. Okay, so we utilize this idea in the music generation from 2002 to 2006. So the information is that the code progression is given. It is not hidden anymore. So the melody is unknown. So we can find the melody. Well, of course, it is a probabilistic process. So we can get almost any melody with a certain probabilistic weighting. So you can take the most probable melody that fits the chord sequence. So this is one idea. But after this, okay, let's move on to the next one. Okay. So this figure shows the chord, the relationship between chord and the melody. Probably you don't need it to hear. Here's a chord change here. Here. And the chord change again here. In this way. So you are fully convinced that in this way. Okay. So the harmony modeling by hidden model is described again in this way. So here's the melody like this, and there's some non-harmonic tones included, like between do and mi. You can it is permitted to put the additional re between do and mi according to the non-harmonic tones rules. There are rules. It is not random. So in some functions, roughly seven types of non-harmonic tones, which is permitted in a harmonic theory. So it can be related to these hidden model parameters. And now it is computationally, so they made on computationally. So we also work is the selection program, like just like in human speech recognition. There's several candidates of code sequences, and you can find the best matching code sequence to the given melody. This is another application. So we were almost the first one to use the hidden mark model in music domain. Not well credited. Anyway, so in such my background, we started automatic music conversion from Japanese lyrics. So melody generation can be done with hidden mark model. But if you are given the lyrics, can you get a good melody for the given lyrics? This is the problem. Okay. So we started the Orpheus project in 2006, and before that, as I have told, 1999, when I joined the JAIST, where Toja Sensei was working already, I joined that institute and started music research with a code progression modeling by hidden mark model. And after some history, and now we have a system named Orpheus automatic music composition system, and we have this kind of statistics. Page view is 23 million page views is recorded. So my first motivation is an application of the hidden mark model derived from the speech research. So for me, it is a kind of very consistent idea to use the hidden mark model. But think again, what is the users want as an automatic music composition system? Okay, so automatic music composition is one of the popular topic in music community. But I think many people are doing the training data and one output and so on, and so they don't care much about the users. What users want. So this is just on my personal view, probably very biased, and some are motivations extracted from my communication with users. Okay, so they care outcome quality, of course. If quality is bad, it is useless, and wide variety. If you have get this almost the same thing, very similar, it is boring. So you need a wide variety and the freedom of lyrics. If a lyrics is restrictions like seven syllables or 18 syllables, something like that, and it needs a rhyme and some style. So it is not free. So we need the freedom of this. So you can put your diary or some article, whatever. And of course, after this, there should be a good match between music and lyrics. Okay, so this is the one topic or one interest for me, and outcome should be their demand is that artistic and unique creation capability. Okay, this is another serious problem, because if you have a very large number of large music database, and you can run a good machine learning algorithm and produce some new piece from it. Is it unique or artistic? So artistic and unique to the user is not guaranteed from the largely training data. So this is the very important point in automatic music creation. And as for users point of view, user interactive adjustability. So if you get one result, if you want to slightly change it, modify it, or improve it, so so system should accept such a demand, a little bit changing. And the transparency is another important factor that user can imagine what is going on in the automatic music composition process. And many people wrote that they lack composition skill, and they hope to have one. And the motivation of utilizing Orpheus system is to improve themselves in composition skill. So it is a serious problem that system, the new automatic music composition system, can help they build up themselves. Okay, and the wide range of we have to care about a wide range of end users, just novice users or very experienced users, and there's a wide spectrum of users, and so we want to cover a wide range. Okay, so before going into the problem solving, simplifying the problem. We had a hypothesis that music elements combine music elements. There are many music elements, and they can be combined to form music, like Lego blocks like this shown there. And so you cannot get the final, the real thing, but you can create, you can make a good creation and produce some prototype. And if you have a good skill, you after creating some new shape or new object, you can do it with wood or anyway craftsmanship. Okay, so it is limited. It is limited, but you can do some unique and creative work. So my formulation, so simple formulation is music is a main melody plus some melody, sub-melody, and two instruments and drums. So that is the goal. The goal is a helpful tool for users. It is not fully automatic. Yeah, of course, it runs automatically if you don't care, but you can interrupt or do some modification to it. And so since the users are involved, the user satisfaction is the number one importance. Okay. Oh, we define the music components as these. Lyrics, of course, given. It is given by the user, and the melody was produced. Harmony, rhythm, accompaniment instrument, and accompaniment figure, percussion patterns, and the timbre on voice. Oh, this is very simple music elements. But the selecting these may produce a huge combination space. Okay, so general audience. Okay, so if you have lyrics like Akai Hana in Japan, that means red flowers. Okay, and it is given, and the pronunciation, the procedure was analyzed to extract by very common TTS technology. TTS is text-to-speech technology, and it has to analyze the input text. In this case, it's Japanese, and we apply rhythm tree. Rhythm tree is for consistency. If you put the timing or the note timing randomly, it doesn't have maybe it sounds very strange. So you have some consistency, but the length of the number of syllables may vary line to line, and so we have some. It is a hypothesis that one of solution is a binary tree that one note is split into two, and the another one is split into two, and then they increase the number of notes one by one. Okay, and so if you take this or even this according to the number of syllables, they sounds. I hope they sound consistent. Okay, this is the kind of cheap trick. But if you have enough number of rhythm trees, it is handicrafted so far, unfortunately. Well, anyway, so user selects on the binary tree structured rhythm family. So selecting a family is the one family can be da 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 da, or might be da 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 something like this, and then you have a consistent tree, consistent rhythms organized in a tree structure, and so you can select it. And according to the number of cells, in this case, the 5 cells, it has 5 cells. So this line is selected to define the timing of these notes. And the second, the next is on the prosodic analysis. Because Japanese is a pitch accent language, one of pitch accent languages. Japanese, I once wondered what's else. Consulting the web pages, ancient Greek and Swedish and Lithuanian are also pitch accent languages, but it is not major languages. And the tone languages like Chinese and Vietnamese can be handled in a similar way. And actually, one of my Chinese students worked on this. But stress languages is not included here at this time. Later, I'll talk about it. So, of course, we can put the range, the pitch range, and the harmonic constraint. So if you have selected this chord sequence, so this time the note should be should have a pitch on the yellow lines at a high probability. But as for non-chord tones are permitted in a certain rule, to keeping rules. So you can find a path. I skipped something. So in a prosodic analysis, akai hana in Japanese is uttered like akai hana, and never akai hana. It sounds like a Kansai dialect, or anyway, it is not a standard Japanese. So in standard way, or if you watch the NHK TV, they speak, announcers speak the akai kana in this way. If you violate this pattern, it sounds strange, and the outcome is not regarded as a good work. Okay. And so I'm talking about the non-harmonic tones area. So in this case, non-harmonic tones is not included, but you can put something in between because passing notes or the auxiliary notes are permitted in the non-harmonic tone rules. And also in this stage, you should be careful that you should not violate the prohibited harmonic theory, prohibition in harmonic theory, like parallel eighths, fifths, or hidden fifths, eighths, and the cross relation. So it is kind of complicated rules, and music school students are spending so much time suffering from the hard time. So that is exactly the reason that it can be automatic. So it is a very hard work for human and music school students, but it should be relatively easy for computers. Okay. I will skip this one. Anyway, so of course you should think of the details to put it in the real calculation. Anyway, so the whole image of the system is like this. So users here and put the Japanese lyrics input and choose the rhythm tree and speed, tempo, and so on. So there are many parameters, but it is not very difficult. Not very difficult. Cumbersome, but not very difficult. So somehow they can do it. And so over the web, our server has these processing parts, and finally creates a sound score and shows to the user. Okay. So the components are something like this. Harmony. As for harmony, you have a choice of from this kind of tables, and accompanying patterns like this. And the unit design looks like this. For example, from this setting, you get this kind of outcome.
緑帽子のおじさんと小さなお猿が住んでいるみんなと仲良しでお猿は何でもお手伝い緑シャツのおじさんと小さなお猿は
So the whole piece is summarized in this table. So it is not very extremely difficult. Anyone can do it. Another example. So one issue is the variety of outcomes. Here, I like this piece. we have the duet function. You have heard, and also the trio. It is not implemented in the web-based system. It is rather hard for even for music school students to write this kind of three voice chorus with the similar with the motives similar to each other and using the almost the same rhythm. Little bit one beat shifted. So this is the concept and write one. It is very hard to anybody. And I wonder how this problem can be solved with a large amount of training data and nonlinear networks. So that I don't deny the network approach, but this kind of rule-based with a probabilistic approach is still how can I say the reasonable anyway. Okay, so if you want, I will play the other examples later. And so we have continued Orpheus related research, and some of them are like this. One is on polyglottal melody generation. So current Orpheus system is specialized for Japanese language, because we are utilizing the pitch pattern rules. But to extend this main issue or main principle of based on hidden map model to other more popular language like English, there is a problem that English is one of the stress languages. There are many stress languages. So here's a very funny example that London bridges falling down. That is no problem. But if the second line is the bridge fell yesterday night, you can you sing it in the same melody? The bridge fell for you yesterday, and something very hard. It's a kind of trick. Okay, so you should collect in the time axis, not a pitch. So this is a quick example we need. So now we try to formulate together. What is a good melody? Okay, good melody is not necessarily the outcome from the large scale training, but it should satisfy music theory, of course, and linguistic requirements. In Japanese lyrics prosody, pitch accent language, and now we step forward to include English and any language. So the general formulation is like something like this, not the code only, but the music theory. So it is a logarithmic likelihood in the logarithmic likelihood domain. It is a summation of these different aspects, and take the likelihood maximum path. It will be the best melody. Okay, so we included music theory and here the music theory and the linguistic aspects, and of course the emotional or the social. So what is popular now and so on. And so you can include this one. I don't know how. So we are doing these two, working on these two terms. You can think of the third additional terms to do a really good composition. And the solution is given by a return path in a second dimensional hidden map model. That is, let's see, this one with time and pitch. So in the current Orpheus, time was given beforehand from the rhythm tree, but now we have time, the freedom of time, and at a certain time resolution, and so you can choose any place, any grid points. So if you choose the real sounds are going to Scarborough Fair or something like that. But if you change it choose these blue points and connect them in this way, it will be a very funny melody. It is also included in the Hillman model, but at a low probability, not prohibited, but not likely. Okay, so this is our formulation. So we can include many rules like non-chord tones and the rules and something, anything. So this can be a good music research issue. How to make a richer in hidden model behavior. And I have the ongoing one of our research is on music completion, meaning that people or a little bit trained people may come up with a good melody, but it's just the fragment. And they know that the second melody should be. Okay. And for some parts, they may come up with a chord sequence. They may have a favorite chord sequence. And let's see. I don't know how to go back from the rhythm. Okay, this is the outcome. Given this fragment of music. So this is a generalization of automatic arrangement or automatic composition. Automatic composition is generalized as this kind of music composition, given some hints and completed in the full score like this. And we are thinking about the interactive Orpheus that will help human users to build up their skills. Okay, with links and suggesting prosody, or which you can correct or intentionally change them. Okay, so it can be a good training for music school students. And the semantics, as you may have watched the poster today, where the lyrics is given, and it is hard to decide on the best conditions of the optional parameters setups. And the other non-core tones we are collecting the database, and other issues like including jazz. Jazz is not excluded. It can be included in our framework. But in the reality, I like classical music. So my system is almost mostly produced classically sounding music. Also, in summary, so I strongly emphasize that the human model is a very useful model, still useful. It is an old model, but it is not it's worth keeping and working on. And Orpheus, we have built an Orpheus system, and we spent 70 years on the same principle. And the next step, we are thinking some issues. Okay, so that concludes my talk. Thank you very much.
Thank you very much. Interesting talk. I'd like to ask you comments, questions. Okay.
Oh, so you want to sit here?
Yeah.
Okay. Another good example.
Question.
Oh, question. Okay. Questions first.
Hi. Thanks a lot for the talk. I'm interested in whether you've ever experimented with some kind of feedback process in Markov models. So, for example, if you take something from the users or outputs either generated by the users or user inputs to change the probability distribution. Is that something you've ever looked at?
Sorry, I couldn't understand that.
Oh, sorry.
What? Users what? Is it feedback or something? Oh.
Yes, I was wondering if if
You're talking about the feedback.
Yes, exactly. Yes.
Mm-hmm. We have not so much feedback, because they are unknown anyway. So they're just users, and they write some comments. So from that comments and their self-introduction, that they are very eager to learn and build up themselves, and that made a motivation of participating in our open experiment of Orpheus.
So for example, I'm wondering if you take, for example, the track that a user has, maybe it's an artist that they like, or like a classical composer they like, and whether you've considered taking data from another music source, and use that as data to bias the distribution in the Markov model. So I'm thinking about kind of a user being able to bias your model towards the kind of music that they enjoy.
Okay, my answer is no, not yet. So we hope to do it, but we don't have to know how to do it, because Bach has a very wide variety of works and the many styles. And if you don't use if you don't have a cluster of the consistent style, the trained results may be funny or something. I don't know, the mixture of waltz and sonata and march and something. If you don't distinguish them in styles, so it is still an open program, not limited within Office program.
Yeah, thanks.
Mm-hmm.
Still a few minutes. You know, to ask? same question to several times. That is, when we hear the first initial tonic chord, then we expect that the music, the melody, will finish at the same tonic. That is, we can have some short-term memory, the memorize, that is a long-distance dependency. How can we implement a long-distance dependency in terms of the hidden Markov model? Yeah. Because Noam Chomsky said that the length of the one sentence of the natural language is almost similar to the time length of the melody, because our hippocampus can memorize such a time length.
Yeah, good question. We have no answer to it. Yeah, it's still an open problem, isn't it? So the remote relationship, so like ABA, how do you create from some the automatic music composition system independently A and again A again?
Yeah.
So there's no good.
David Cope uses good results. You know, David
David Cope, yes.
Yeah, David Cope captures structure very well in his system.
Cool.
Yeah, David Cope.
So
So he's now retired UC Santa Cruz.
did he give a general solution to that problem, or in his specific system?
So I can't remember the specifics, but he calls it augmented transition network. So in comparison to Markov, it's one-dimensional. So he uses augmented transition network where he connects everything to everything.
Yeah.
And so somehow it captures form.
Okay. Yeah. So
he does very good at form capture.
Yeah, I think that again, it can be another simple solution to it. Okay. So I corrected my answer. So there's some popular, well-known solutions. Now that can be applicable to this, but anyway, currently we don't use that way. And there's no reason that there's four phrases, and the 1 and 3 may have the same melody. Share the rhythm. We don't do that.
Also, the form is often pre-composed, so you can impose on.
Like as for the structure, yes, it is. It is possible. But it may mean that to violate the prosodic requirements. And so, if you or anyone have a good way to compromise them, the different multiple requirements, that will be a solution. And actually, we are thinking of the finding the beat path for the shared lyrics at the same time, parallelly one, and they find the solution or the common shared melody, that makes the sum of these two likelihood to the summation is maximum. So this we come up with many simple solutions, but now we are running a fairly large system, and so we didn't change it so often. So that's the reason.
Okay, just a very small question. If you would like to know why your system is named after the Greek legend Orpheus, why named Orpheus?
Sorry?
Why your system is named Orpheus?
Okay. Good question. Let's see. There should be enough. Oh, sorry. I wanted to show you the image of Orpheus. Orpheus is Greek, the god, in a Greek myth, and he is a very good player of musical instrument. Yeah. And there's a sad story that his wife, the new bride, was bitten by a poisonous snake, and passed away. And so the Orpheus went to the hell. Hell? Is it right? Yeah. And what is the good word? Negotiated with the Hades. Yeah. And so finally, so he was able to bring back his wife. But on the way, on the condition that he never looked back to him to her on the way before coming back to the earth. But he did that. So there's that made an opera like an Orpheus group. Yeah. So because of the LDDJ or Eurydice asked eagerly, why don't you look at me? You don't remember me or something like this. And so from the deep love, so Orpheus looked back her before coming back to the earth, and then the LDDJ disappeared forever. So that is a sad story, very impressive sad story with a good music player. So that's the reason I chose the film. So this is the answer you wanted?
Yes.
Okay.
Yes, sure, of course.
So I don't want the sad ending with the Orpheus.
Okay, so somewhat persuasive. Okay, later, because the time is up, ask the coffee break. So let us thank him again with a big hands.
So I pray them and vote. This is why I emphasize HMX so much.
Please indicate how you may feel like, it needs a coffee break, but if you'd like to, please stay here.
Another unusual one.
Well, now they're retired. He used to like that once a year. He likes to doctors.
So what do you think the future will be like? Because you are using classical method, but so many networks, many based people.
My name is Tomoyasu Nakano with AISP Japan, the organizer of this session. So we have two papers of this session. So the sending information processing. So the sending information processing is important not only from the academic perspective, but also important from the industrial application perspective. So we have two papers. So let's move on to the first paper. The title is towards potential applications of machine learning in computer-assisted vocal training, presented by Antonio Stadler, Emilia Parada-Cabreiro, and Marcus Schüler, and presented by Emilia. So please.
So hello everyone, I'm Emilia, and I'm going to present this paper which was mostly performed by my bachelor student, Antonia, and it's also a collaboration with Marcus Schüler. So I come from the Department of Music Pedagogy at the Nuremberg University of Music in Germany, and my co-authors come from the Institute of Computational Perception at Johannes Kepler University Linz in Austria. So the use of technology to support the education is already established in general. In music as well, we could have seen in the sponsored talks very nice examples from piano teachers at Pitina who use technology to support their students. And of course, singing is not an exception. So from an educational point of view, there are many teachers and students who are using technology to enhance the learning process. And typically these tools are based on enhancing the learning by visualizing the voice and understanding better. And obviously also from the informatic point of view, there is many interest and always more works in the realm of machine learning. We have seen a lot of increase in the use of technology and developing also new tasks. For instance, recognizing the quality of the singing, but also automatic recognitions of techniques. However, when introducing AI in the educational pipeline, there are some problems. And the main ones I have seen so far are of both sides, so from the pedagogical point of view, but also from the computational point of view. So let's take a look at the educational ones. So when we look at the schools, the students and teachers in the musical domain, they often lack of computational or AI expertise, and because of that, they don't fully understand which are actually the goals, what should they become from this AI, and since they don't see really usability, they don't spend the time using the tools. Often the teachers are also afraid to use technology because they are afraid to be replaced and to lose their jobs, and this is the reality, which comes just for not knowing really the technology. On the other side, also from the computational point of view, there are some problems at the moment. So the main criticism that we can find in the literature is that there is a movement or a technocentrism where the computer scientists develop tools which actually lack of pedagogical motivation. So it's not really clear what is the goal of these tools, or the goal itself is actually the tool, while the tool should be simply an instrument to be used to enhance the learning process and not to really replace it. So with this background, we have made a study which is very preliminary and aims to evaluate actually how could we find compromise between these two different disciplines, so music pedagogy and also computer science. And we focus here on the task of singing technique of recognition, and we base our study on the assumption that by comparing machine learning performance and human performance, we could get some insights of actually what might be useful or where are the tools right now and how could they be integrated in a learning process. So our research question is, the main one is to evaluate how different features or presentations perform in comparison to different learners' level. This means that we are comparing perception with machine learning by guaranteeing comparable setups. We are using the same features for the models and for the individuals, and we are also comparing or taking into account different learners levels, so advanced and beginners. And we aim, by doing this comparison, to be able to start to have some hypotheses on how could we really implement then a tool which is useful for teachers and students in a real application. So let's go to the methods. The dataset we used is a well-known dataset in the Maya community. It's the vocal set, and it has been presented, I think, 4 years ago at Izmir. And it contains a lot of different samples of singing techniques performed by professionals. We used a subset of it, as well as the authors made in the official baseline, to be able to compare our results. And this means that we use only 10 singing techniques, and they are produced by 11 males and 9 females. And our test set contains 2 female and 2 male. This test set is the one used to evaluate the models, and it's also the one used to perform the user study. This is important because then we can compare one by one the human's performance with the machine learning performance. And as you can see, there is a huge unbalanced distribution of samples across techniques. This is how it is. We cannot do anything about it. We know that this has impacted the performance of the models, but we will evaluate the results with the unweighted approach recall metric in a way that we can still fairly evaluate what we have got. Alright, so the methods, let's start from the user study. So we have performed 2 different user studies. One is for the advanced users, and they perform the auditory task. So they are musicians, and they are able to recognize the techniques by listening to them, because they are trained musicians, trained learners. 20 people participated in this study, and they annotated between 25 and 80 audio samples each. On the other side, we have the visual task, where the participants annotated the spectrograms. They had to look at the pictures. And this task was performed by non-trained musicians. Since it takes much longer to do this task as the other one, we recruited double of people in a way that we can still be sure that the results are accurate and we can trust it. So, as you see, we have different learners for different tasks. That is obviously a limitation because we cannot compare both groups, but this is not our goal. In the study, what we want to do is to compare the users with the machine learning, and the decision of doing this was simply because we didn't have enough resources to make both tasks with all the people, so by both groups, and that way we just took a pragmatic decision and decided to encourage the learners in their capacity. So we are evaluating each type of learner for what they are able to do. So the beginners will be totally unable to do the auditory task, so it will be totally unreliable. So at this point, we just decided to encourage each learner with the task we are going to evaluate. So the task was user study, so very simple in the web. So they had to listen to the samples and select just one technique. Obviously, at the beginning, there was a training phase where the participants will learn or will understand what was expected, and they could listen to the sample as much as they could. So this was for the audio, and the other one will look like this. Concerning the models, as said, we are going to evaluate the audios and the images, so we extract visual and acoustic features. So the acoustic features, we extract the different ones and also train different models at the end. To be fair with respect to the users, we are going to also encourage here the model, and we are going to show the results which were best for both types of features and compare those with the users. So for the audios, the best features were the MFCCs, and were used for the CNN, which was actually the same model used in the baseline of the paper. And then with the spectrograms, we just got that the RNN, very simple, was the best one. So let's go to the results. I will present first those for the auditory task, then for the images, and then compare both. So here we have a confusion matrix. In the diagonal you have the records. As you can see, it's very much highlighted. This means that the users perform pretty well. They were able to recognize the techniques, some of them perfectly, so they didn't make a single mistake. And this could be to some extent expected. They were advanced students already. Then we can see that there is a technique which has a quite low precision. So the horizontal line below is the precision, and this is trill. The reason why it's not so well recognized is that there is a prominent confusion pattern with the techniques trillo and vibrato, and this can be understandable. They are similar, and this made also that vibrato was pretty badly recognized by ear. So when we look at the images, we now see that the diagonal is not anymore visible as before. So in general, they perform much worse than would also be expected, like they are very beginners, and they still, again, two techniques are much better recognized. And we see Trillo, okay, is again with a very low precision, but many other techniques are as well with a very low precision, so that's in general the case. So there is a huge confusion everywhere, and this is the reason why the values are spread everywhere in the matrix. So we have again this confusion pattern, which is among the named techniques, the trill, and vibrato. But now actually vibrato is the best recognized, which are pretty high precision considering the rest of the techniques. And this is interesting because it might suggest that this technique could be better recognized by watching at the images, and we will see in a minute whether this is true or not when comparing with the machine learning results. Okay, so when we compare the results for the altitude task, so machine learning with the advanced students, we see that we can mirror to some extent the results of the user by the machines. Again, the confusion pattern is there. It's not totally mirrored, but for two classes. And it is true that vibrato is again not so well recognized, but here we should note that the confusion is with another class, so we cannot really say we are able to reproduce the results of the people with the machines, because it's not the case. Concerning the images, again, some of the classes are also kind of the same recognized. The confusion pattern is again there to some extent, not completely, but most interesting is that vibrato is quite well recognized here, much better than for the audio. So this means that we confirm actually that this technique is much easier to be recognized from the images than from the audio, and this is interesting for our future work. So jumping to the second, how can this be useful for us in an educational context when we are developing tools? So on one side, we have seen that since machine learning performance outperforms non-trained users, so the models were better than the beginners, machine learning could be used to support beginners especially. This is not the case for the advanced, because the advanced students are much better than the models, so it would not make really sense to do a game, for instance, because the students will always win. On the other side, however, since some feature representations are more useful for some techniques than others, for instance, recognizing vibrato through images and not through audio, the idea here will be that we could combine cross-modal exploration to support learners to understand ambiguous classes, for instance, vibrato 1. So now, in base of these results of these reflections, our goal or our idea is that in the future, interesting will be to implement an interface based on explainable AI that could be probably the best solution to support everyone. So on one side, the beginners might be supported by having a kind of game for very basic classes which are not ambiguous, and this could increase their motivation. But we should be careful about that, because if the class is ambiguous, the student might get more confused than before. So when implementing such a thing, we should be careful about not so clear classes, because there is sometimes between two classes that are similar, it is not like white or black. There might be a gray zone which is not really clear. So in such a cases, for advanced users might be actually useful to integrate some kind of explanations which will say, okay, this class is ambiguous, but if you look at the spectrogram, then might get more clear, and also to include always a confidence parameter that tell explicitly the user, look at this class is ambiguous for you, but also for the model. So it's an objective, actually, not clear, so it's not clear at class. So that was from my side, actually. So thank you so much for your attention.
Thank you for your interesting presentation. So any questions? So can I ask you something? So could you explain again about how to see the confusion matrix on the user study 1 and user study 2? Yeah, this one. So user study 1 is for trained listener.
Yeah.
Trained listener listen audio only, and they recognize which technique was used in this singing voice. Okay.
Yeah.
So in this case, so the straight technique is, I think, relatively low. So why is this means that 62% is the performance to recognize straight.
Yeah, this is a call.
So why so straight is difficult to recognize it?
It might be because of the different samples used. So all the techniques were performed with some scales, with some intervals, so different melodic patterns. So that might be a reason why that. I was also surprised that actually vibrato was so badly recognized. Then I realized, okay, it's because it's quite confused with the trillo one. But I guess it depends on that, on the type of melodic which is included in the dataset, because as said, it's very unbalanced. So it could be that the users might be penalized because some of the techniques are only available for one melodic pattern, while others not. So maybe the listeners started to associate unconsciously one technique with one melodic pattern, which is not right, actually. But it's true, it's the data we have, so we should put more effort in developing more data set of that kind.
The stimuli has a kind of melodic patterns.
So they had to perform some melodies, scales, or arpeggios, or repeated notes. That was in the data set, and then repeat each technique with that. I think, except for the spoken one.
Oh, okay. So thank you. And also, so how about the user study 2? So it is for untrained listener. So they see the spectrogram to recognize singing techniques. So this is also straight is very low performance. So
yeah, I mean this part was, I think, really hard because the students were absolutely beginners, and they were also evaluating a spectrogram. Some of them didn't know what that was. It was a really long part at the beginning trying to explain what was expected with a lot of examples, but it could be that the task was really, really hard. We discussed a lot how should we handle the situation, and we got a lot of criticism from the reviewers because we are comparing two trainer levels who are actually performing two different tasks, and that's a huge limitation, we know it. But when working with people, it's extremely hard to get access to them and perform the tests in a reliable way. So
I think this kind of spectral reading is very difficult for even for trained listeners.
Yeah,
was there any pre-training?
Yeah, there was an initial phase where the users will have all the examples and have time to try to identify them, but it didn't last more than 10-15 minutes. So we think that this is definitely related to the fact that it was difficult. And they even said, we made a questionnaire in the end, and they said things like, sorry, I'm a musician, or I'm trying to be a musician, I don't have any idea what all these technical things or spectrograms are. So there were complaints about that.
Okay, thank you. So, any questions? Oh, please.
Thank you for the interesting presentation. So, I have a question about the audio example for some use for stimuli for the participants. So actually, do you consider the quality of the audio example that were fed to participants? Because actually, I am another person who is using vocal set at my own research, but actually I found that some of the there are some, what to say, inappropriate examples, such as, for example, even if the label is Toledo, but actually some actual examples are failed to produce Toledo, it gets more like vibrato. So how about this? So did you take the samples?
So we selected the samples actually by trying to have enough samples, so from each performer. So the goal was to have a test set which included all the singers performing all the techniques. So that was a big constraint. We listened to the test samples and they were, concerning the quality of the audio, were okay. Concerning the technique is what I tried to explain before. Sometimes in such a task there is not a really clear ground truth, so we could aim more to a gold standard. So there are some classes which are not so clear, so they are not okay, that's black and that's white. There are a lot of gray zones which neither the people can say, okay, is this A or B? And of course in this part is difficult, and when working with this in an educational context we should be careful, and that's the reason why I highlighted that when we try to use AI in this context, we should include a confidence barometer metric which tells the user explicitly, okay, you have got it wrong maybe, but look that this is objectively not clear, so don't be discouraged. It's something actually to think about and be critical yourself.
Okay, thank you.
Okay, so it's time's up. So thank you so much. Thank you, Emilia. So. Okay, let's move on to the next paper. The title, the text of Convolutional Autoencoder Bottleneck with on StarGAN-based sending technique conversion. The presenter, Tomoyasu, Yong-Chuan-chan, and Iwen Liu, so presented by Tomoyasu.
Hello everyone, I'm Yong-Chuan Zhang from National Tsinghua University. And this work is done by Dongchen Su, me, and Professor Iwen Liu. And our research is titled Effects of Convolutional Autoencoder Bottleneck with StarGAN-based Scene Technique Conversion. So first is our main task, Scene Technique Conversion. Scene Technique Conversion is a task of converting only the scene technique of the scene voice, while keeping the linguistic content, the melody contour, and the singer identity. And here is one example. This is our source voice. It's in falsetto. And this is our target, and this is our converted results. The target technique is chest voice. So we can hear that the voice is more intense and forward, similar to chest voice, but it still sounds like it's sung by the same person and the lyrics is the same. And the reason we want to do scene technique conversion is that within scene technique is an integral part of vocal performances. The same musical phrases sung in a soft head voice or belted have very different effects. And the second is that scene technique conversion is less research. Most scene voice conversion researches are focused on singer identity conversion. And next is our main question we want to answer in our research. So in order to perform scene technique conversion, we use convolutional autoencoder. It has 3 modules: the encoder, bottleneck, and the decoder. The input is compressed by the encoder and through the bottleneck and decompressed by the decoder into the output. And the width of the bottleneck is the latent spaces dimension, the dimension of the conversion process. So the size of the bottleneck is related to what features will be converted and affects the voice conversion results. So our main question is how to design a convolutional autoencoder bottleneck for scene technique conversion, and more specifically, how does the width of the bottleneck affects the results of scene technique conversion. And here I'll introduce our system for experimenting bottlenecks and scene technique conversion. So this is a general block diagram of our system. We use word vocoder for audio analysis and audio synthesis, and we use StarGAN for conversion. We use word vocoder to extract spectral envelope, aperiodic parameter, and fundamental frequency. Only the spectral envelope and aperiodic parameter are used in conversion, since we want to keep the melody of the singing voice. And we use StarGAN as our main model for conversion. It has 2 main advantages. First is that it's multi-domain. Traditionally, we need 1 model for each domain-to-domain conversion. So in our case of using 4 domains, which is chest voice, falsetto, whistle voice, and raspy voice, we will need 12 separate models, like the A plot. But with StarGAN, we only need 1 model for all conversions. This reduces the training time and resources we need for the task, and also forms the cool star-shaped plot. So the second is you can use non-parallel voice data for training. Non-parallel data means that we don't need to have the same musical phrase sung in each domain and align in time. We have some songs only sung in 1 domain and some in the others, and we can still use that data for training. This simplifies our data recording and pre-processing, allows much more freedom for the singer to choose what they want to sing. So the next is a brief explanation of how StarGAN works. StarGAN is trained using 3 losses. The first is adversarial loss, which lets the model to generate results that is more similar to real data. And the second is classification loss. Besides discriminate between the real and the fake results, the discriminator is also tasked with classifying the results into one of the domains. So the goal is to have the results to be classified in the target domain. And this loss will help the model do that. And the third is reconstruction loss. This means when the model is given the same technique as source and target domain, its output should be as close to the input as possible. This makes sure that the model don't change the feature that we want to keep in the conversion process. Since linguistic content are usually the features that should be the same in most voice conversion tasks, we think that reconstruction loss is related to articulation clarity of the results. And finally, this is the generator used in StarGAN. We use the attribute, the green space, to set our target. And we focus on the bottleneck part for our research. We want to change the size of the bottleneck while keeping other parts of the model the same. We choose 3 bottlenecks for our experiment. And so we keep one of the size dimension, the height, the same, while changing the channel numbers and the other size dimension, width. And because we want to use the same kernel size and other settings for encoder and decoder, we use the numbers of up and down sampling layers to control the size of the bottleneck. With more layers, the encoder compresses more, the bottleneck size is smaller. So next I will talk about how we experiment with the 3 bottlenecks and the singing technique conversion results. First, we recorded our own singing technique dataset. We recorded 2 female and 2 male singers. They sang in 4 techniques that's common in Chinese Mandarin pop singing. And we choose 3 vocal registers, the first 3, and 1 distortion method as our techniques. So chest and falsetto are probably 2 of the most common techniques used in pop singing, and chest voice is closest to speaking voice. So here's an example. And falsetto usually sounds softer. And whistle voice is really nasal and has really high pitch. So let's hear it. So this technique is more common in singing competition for the singers to show off their skills, since one of the singers we recorded can sing this, and we also want to test the conversion system's limits. So we choose this as one of the 4 techniques. But because of the unusually high pitch range, the results with whistle voice as source or target technique is pitch shifted to a more probable range. This is the only technique that we perform pitch shifting. And the 4th is raspy voice, which is a heavily distorted voice. So after we use our dataset to train the 3 models and generate the results, we recorded 27 participants to do listening tests to evaluate our results. First, we asked the listener to compare the results produced by the 3 bottleneck size models from the best to worst based on articulation clarity and conversion performance. Second, the listener is given the original audio and converted audio and a clip of the target technique, and asked to rate how similar the converted audio is to the target in terms of timbre. So for this and the next part, we use the middle-sized bottleneck for conversion. Since when we were testing, we thought the middle size sounds the best, and we will see if the listening test results agrees with us. And last part, we use a 5-point scale mean opinion score to evaluate the sound quality of our results. We ask the listeners to rate the converted results and the results of using only the vocoder but not StarGAN, to compare how much the conversion model affects the sound quality. And here is our result for bottleneck comparison. We use a point system where 3 points correspond to the best, 2 to the middle, and 1 to the worst model. The score here is the average of all the participants' responses, and the error bar is standard deviation. Generally, we can see the 2 layers is better. And we can listen to the results for articulation clarity. Here is the 2 layers result of falsetto voice converted to chest voice. And this is the 3-layer result. And the 4-layer result. I think for the 4-layer result, it is clear that the clarity is affected by the conversion. Some of the words are completely changed, but the 3-layer result also has some vowels that sounds different. But we can see that in conversion performances, however, 3 layers model actually outperform the 2 layers model in some cases. And here's an sound example. This is the 2-layer result. And this is the 3-layer result. And a 4-layer result. First, note that the conversion is from raspy voice to falsetto voice. So the source is a really strong and intense voice, and the target is a really soft and quiet voice. And we can hear that in the 3 and 4 layers version, the intensity is lower, so the model is able to convert that. But in the 2 layers version, the models it still sounds really strong. And also the 4 layers result sounds more nasal, which is also more similar to falsetto. And the 2 layers version also has some artifacts which make the result sound more metallic. So overall, we think that even though the 2 layers is better most of the time, in some cases there seems to be a trade-off between articulation clarity and conversion performance, meaning that a smaller latent space might affect the linguistic content, but the conversion is easier. And a reminder that we only use the 3 layers model for the next 2 tests because we, the authors, thought that it sounded the best before the listening tests were done. So it is actually a surprise to us that most listeners find the 2 layers model to have better conversion performance. And next is the results of likeness to target tests. You can see that although the scores vary, most of the results are more similar to a target technique than a source technique. And here we divide the results with source and target technique. One interesting thing is that falsetto is the best performing source technique, but the worst performing target technique. This indicates that the features of falsetto voice might be less prominent perceptually compared to other techniques. And the opposite of that is whistle voice. It's the worst performing source technique, but the best performing target technique, which also indicates that the features of whistle voice might be stronger perceptually. Also, whistle voice is the only technique where we use pitch shifting. Using whistle voice as source means that we need to shift to lower range. Here's an example. And using whistle voice as target means that we need to shift to higher range. So whistle voice performs the best as target technique also means that pitch range might be an important factor for a human to classify technique, as its distinct pitch might be the easier to recognize and therefore the conversion is better. And last is the sound quality test. We can see from the score that the converted results have worse quality as expected. However, the vocoder only score is lower than we expected. We think this is caused by the distortion of the raspy voice and some of the breathy falsetto and whistle voice parts being classified as from a voice by word vocoder. So this means that although word vocoder is good for separating fundamental frequencies so that the melody is unchanged, neural vocoder might still be better in regards to sound quality for singing technique conversion. And finally, our conclusion. So we performed singing technique conversion on 4 singing techniques, and we found out how convolutional autoencoder bottleneck affects singing technique conversion. In the model we tested, the 2 layers bottleneck size is usually better, but there's a trade-off between articulation clarity and conversion performance. And this is my presentation. Thank you for listening.
Thank you for presentation. So any questions? Oh, please.
Thank you very much for the very interesting presentation. I was wondering about you presented results asking people if it's closer to the target or closer to the source voice. And when you presented the example, converting from, I think it was raspy voice to falsetto, right? Immediately I thought, oh, I don't know if I would be able to tell that the target is falsetto. And I'm wondering how well-trained your listeners were in recognizing those singing techniques in the first place.
The listeners are non-trained, so they are normal people, not professional singer or anything like that. So yeah. So they probably don't know that the target is falsetto, but they can compare the target audio and the converted audio, so how similar the timbre is. But they probably don't know the label that of the voice is falsetto.
I see. So they have the audio samples to listen to, and then they say it's closer to this or closer to that.
Yes.
I see. Okay. And the same goes for the other test that instead of considering the target, it considers the source, right? They also listen to the.
Yes. Yes.
Okay. Thank you.
Thank you. Any questions? Please.
Thank you for your presentation. I'm just wondering about the relationship between StarGAN and CycleGANs, since we're talking about a style transfer task. Does it have some similarities in the loss and the constraints of the generator?
I believe StarGAN is based on CycleGAN, and they changed something, and so yeah, so it's CycleGAN first and StarGAN.
Okay. Thank you very much.
Thank you. Any questions? So can I have one question? So, did you you didn't use zero changing for the conversion, right? So is it possible to convert chest voice without changing F0 to the voice to voice? I mean, voice to voice is usually very high pitch, but chest voice usually are not high. So is it possible? I was wondering if it's possible to change this normal chest voice to the whistle voice without changing F0.
So we tried that, and we think the result sounds really weird. So we didn't include in the test. So even because the pitch is a integral part of whistle voice. So when we change chest voice to whistle voice, it sounds actually similar to. This is the whistle voice pitch down. So it's really nasal. So when we transform the chest voice to whistle voice, but not pitch shifting up, it sounds similar to this. So
I also wonder if F0 changing high, so the quality will be better. So I think.
Yeah. So that's why we only use pitch shifting in whistle voice. So the chest and falsetto and raspy voice, we collected data in similar pitch range. So because we think pitch might affect the results, but whistle voice we think we can try a really high pitch one.
Okay, thank you. So it's time up. So thank you so much for your presentation. And the session is now closed, so I'd like to thank all the presenters for their presentation and all those who participated in this session. So thank you so much.
Okay, this is an announcement from organizers. All these things are left. Demo room, the mouse, the cap, and the coat. Oh yeah, yes. Very pretty. I don't know what. Black beret, black mouse. If you, someone. Okay, I place here. And second notice is that.